This will be the first of 2 lectures over periodic properties of the elements, and this first lecture will be over the size of both atoms and ions. So first, just to make sure you understand the periodic law, that's just a basic kind of vocabulary definition, and it starts back with Mendeleev, who was the first one to try to arrange the known elements in some type of order. He arranged them by atomic mass, and remember that that's not how they're arranged in our current periodic table. In our current periodic table, they're arranged by atomic number. So, but he did find, when he arranged them even by mass, that there appeared to be properties that repeated. And now we know that the properties that repeat occur with elements that are in the same family or the same group. So elements all in group 1, for example, have similar properties, whereas elements in group 2 have similar properties, etc. And the reason those properties are similar is because elements in the same group have the same number of valence electrons, that is, electrons on the highest energy level. And it's these valence electrons that do the chemical reacting, so they determine a lot of the chemical properties of the elements. All right, so just to kind of review some of the basic classification of the periodic table that you should already know, group 1 is called the alkali metals. Group 2 is alkaline earth metals. Actually, that should be, I just noticed that misspelling. That should be, for group 2, alkaline earth metals. The whole middle group is transition metals. And then the important groups after that are halogens that you'll hear named frequently anyway. The halogens, which is group 7A, and the noble gases, which are group 8A. And we have what the F block, or the rare earth elements, which are called lanthanides and actinides. But the one thing to remember from this, besides some of the names, is that the number of valence electrons an element has equals its group number. So group 1A has 1 valence electron. Group 2A has 2 valence electrons. Transition metals are just weird. Everything's variable with them. But skipping on over to group 3A, the boron group, they all have 3 valence electrons, etc. On and on to noble gas family, which has 8 valence electrons. Well, you might be asking yourself, as I probably would be, what's the purpose of periodic trends? Why do I have to learn this? Well, chemists, instead of having to look up every single individual element and all the zillion properties it can have, can at a glance look at the periodic table, and because we have what we call periodic trends, we can estimate the approximate reactivity or the approximate size or how hard it's going to be to remove an electron just by knowing the trends and in what direction they go. And so that's kind of the usefulness of periodic trends to chemists. The trends that we're going to look at are atomic radius as well as ionic radius. That's in this lecture. And then in the next lecture will be electron affinity, ionization energy, and electronegativity. Those last 3 are all kind of related to one another. All right, so the most important concept, so if you're kind of daydreaming or watching TV, tune back in for a minute. Most important concept in understanding periodic trends is to understand the effective nuclear charge. That is abbreviated, I call it ZEF. That's not what chemists call it, I am sure. But capital Z stands for atomic number. It represents different elements. And then this EFF is for effective nuclear charge. Let me give you the mathematical formula for ZEF first, and then I'll explain to you what it is. So ZEF, the formula for it, is the total electrons in an element minus the core electrons. What the heck do I mean by core electrons? Well, I think you know what valence electrons mean, right? So core electrons are all electrons that are not valence electrons. So it's all the inner electrons are the core electrons. And so what is this formula saying? is saying the effective nuclear charge. Now remember, a nucleus has a positive charge in it, right, because of the protons. So the effective positive charge that electrons feel is equal to the total electrons minus the core electrons. Let's look at an example. I think it'll help you understand it the best. Here's a Bohr model of phosphorus, okay? Phosphorus has 15 total electrons, has atomic number 15. It turns out that how many core electrons does phosphorus have? I'm going to circle them. 1, 2. Remember, core electrons are the inner ones. They're not valence. 5, 6, 7, 8, 9, 10 core electrons in phosphorus. 10 electrons are not valence electrons. Okay, so according to the formula I just gave you here, Zeph, or the effective nuclear charge, is 5. It's 15 minus 10, and that's effective nuclear charge of 5. What that means is these valence electrons in phosphorus, in the outermost energy level, only feel 5 protons from the nucleus because of all of the interference by these core electrons. Okay, so what's important in all the periodic trends is the effective nuclear charge that valence electrons feel. That you'll be able to explain a lot of trends away by understanding effective nuclear charge. And I will say right now that probably 95% of doing well on periodic trends is understanding the concept. There's really no math involved. Why do we care about effective nuclear charge? Well, what's holding the electron in an atom? It's its attraction to the positive protons in the nucleus, okay? And what's working against that attraction is the electron-electron repulsion from other electrons. So it's kind of a tug of war going on. And as long as the effective nuclear charge, as long as the attractive charge is larger than this electron-electron repulsion, that atom will be in a good energy state. All right, so what does Zeph do as you move left to right across the period, or top to bottom down a group? Well, the effective nuclear charge that an electron feels increases from left to right across a period. So I want you to think of, let's say, period or energy level 1. Okay, what happens as you go from hydrogen to helium? Okay, that's energy level 1. Okay, why would the effective nuclear charge increase going from hydrogen to helium? Okay, besides just looking at the mathematical formula, what's the difference between hydrogen and helium? Of course, you're adding an electron, a neutron, etc., but most importantly, you're adding a proton. Okay, and of course, as you add a proton, the effective nuclear charge is going to go up. And that simply explains, that's very simple, why Zeph, or effective nuclear charge, increases left to right, because you're adding protons. The effective nuclear charge decreases going down a group in the periodic table. That's not really hard to understand either. If you look at a couple Bohr models, let's look at hydrogen. So we've got the nucleus, and it has 1 energy level. And then let's look at lithium. Here's its nucleus, and it's got 2 energy levels. All right. So if you're talking about hydrogen, you've got an electron, and the valence electron is pretty close to the nucleus and feels a pretty strong Zeph, effective nuclear charge. The valence electron in lithium, on the other hand, is 1 energy level farther away from the nucleus, does not feel the full effect of the nucleus, and so its Zeph, effective nuclear charge, is going to be lower than that of hydrogen's. So Zeph in general decreases going from top to bottom down a group. All right, the other effect other than Zeph that you have to consider in my guess, there may well be a short essay question on the next test about understanding conceptually periodic trends. So as much as you need to go back and forth between effective nuclear charge and shielding until you understand them, I would recommend that. All right, so shielding, we've kind of alluded to it already, but basically, let's say you have a nucleus, and this little drawing here, this dude playing music is representing our nucleus, and everyone's attracted to him, wants to see what he's doing. And the valence electrons, we're going to say, are out here. The people that have the cheap seats at the concert, they're kind of far away. And all of these people in here are the core electrons, and the core electrons shield. Okay, that's the term we're trying to understand. Shield these valence electrons from getting the full effect of the concert. That's what core electrons do. They shield the valence electrons from the full attraction of the protons in the nucleus. And so that's another term you need to be able to understand and incorporate in any type of conceptual explanation that you give. All right, so let's actually start talking about trends. This lecture is about atomic radius, and the last couple slides are actually ionic radius, which actually you'd think they'd be about the same, but they actually are somewhat different. So for each trend, we will talk about the trend from left to right across a period, and we will also talk about the trend from top to bottom down to group. Okay? So atomic radius, what does it do left to right across a period? It actually decreases, size gets smaller left to right across a period. You can represent this two ways. You can represent it like I'm drawing with this arrow pointing from left to right and saying decrease, or some people prefer to describe all trends in terms of which direction it increases. So if that's the case, you may see an arrow pointing in the direction of increasing. As long as you write the correct word over your arrow, you're saying the same thing. But the bottom line is, what surprises a lot of people is, here, if you look here, the size of these pillars represent the size of the atom. So the taller the pillar, the larger the atom. Why, oh why, would an atom, an element on the left side of a period, be larger than an atom on the right side of that same period? Okay? You're adding stuff. You're adding subatomic particles. You're adding protons and neutrons and electrons. Why, oh why, is that atom getting smaller when you're adding stuff? So that was, as you can imagine, a huge mystery. And so I'm going to make an attempt to explain it. All right, so as always, it's easiest to look at period 1. And so we're going to look at energy level 1, period 1, with hydrogen and helium. And I just wrote the electron configurations just to kind of help you identify them. And hydrogen only has one proton in its nucleus. It's atomic number 1. And helium has 2 protons in its nucleus. It's atomic number 2. And so let's look at hydrogen first. It has 1 proton in the nucleus, and so the attraction that the valence electron feels, or the only electron feels for that nucleus, is, we'll call it X. Okay. Along comes helium. It now has 2 protons. It effectively has twice the attraction for the nucleus as hydrogen does. Here you have a valence electron, and it is feeling roughly 2 times the electromagnetic attraction to the nucleus as hydrogen. So what's going to happen when you feel more attracted to something? It's going to draw you in closer. You're going to want to get closer and closer to what you're attracted to. So the whole atom shrinks down so that the valence electrons can get closer to the nucleus. And so this dotted line that I have here represents the original size of the hydrogen atom, and the hard black line represents how much it has shrunk down because of that extra electromagnetic attraction. And so the bottom line is, going left to right across any one individual period, the atomic size is going to get smaller. All right, so let's look at a type of graph that's very commonly presented to talk about periodic trends. So in this case, again, the trend in atomic radius. They have, when they say main group, that means everything but transition metals, because they always behave kind of weirdly. It is organized by atomic number across the x-axis. So of course we're starting with hydrogen has atomic number of 1, then helium, lithium is atomic number 3, and etc. Just so you can kind of get your grips on what's being graphed here. Along the y-axis is the radius, which you can simply think of as size. That's a measure of the size of the atom. And so as we're going from hydrogen to helium, the size is going down, just like I discussed. But then these first two are in energy level 1. What happens when we go to energy level 2, which starts with lithium? Okay. Energy, level 2. So lithium through neon is energy level 2. So what's happening to the atomic radius, the atomic radius or the atomic size going from lithium to neon? That's, if you look at a periodic table, lithium to neon is going from left to right across period 2. Well, of course, the size is going down again, just as we saw with hydrogen and helium. And that's true in any energy level or period on the periodic table. The size is going down. So that trend repeats itself. Okay. So now let's talk about what happens to size when we go from top to bottom down a group. So think a minute, what would you think would happen to size? Instead of going left to right across a period, if we went top to bottom down a group, and this graph is probably not a good one to understand that because it feels opposite. But if we're talking about, let's say, group 1A, that would involve hydrogen, lithium, sodium, potassium, rubidium, and cesium. So if you just want to look at a group, this group 1, for example, are those elements. Okay? And so if you look at group 1, it's clear that the radius or size of the atoms are getting larger and larger. So cesium, for example, is at the bottom of group 1. You would expect, I think, that the size of an atom way down there would be much larger than the size of an atom toward the top. Now, why? If you were needed to explain that in a short essay question, how would you explain that? It's simply that what happens as you go top to bottom down a group, you're adding energy levels. With each step down in the periodic table, you're adding energy levels, and with each energy level, you're quite a bit farther away from the nucleus and you're quite a bit larger. So I'm going to try to draw some Bohr models for you in the next slide so you can visualize it a little bit better. Okay, so this is looking at group 1A in the periodic table. It's the alkali metals, and it's looking from the top to bottom down group 1A. So we start with hydrogen, then we have lithium, sodium, potassium, etc., but I ran out of room. Hydrogen is in the first energy level, okay, energy level 1, first period, and so it only has one energy level of an electron around it, okay. Lithium is in energy level, starts energy level 2, or period 2 in the periodic table, and there are 2 energy levels, and so of course lithium is going to be larger than hydrogen. Sodium is energy level or period 3 in the periodic table, and so there are 3 energy levels, and so it's even larger than lithium. And same trend with potassium. Potassium starts energy level 4 or period 4 in the periodic table, so there are 4 energy levels to deal with, and it's even larger. So it's pretty easy to understand why the size of an atom increases going from top to bottom down a group. You're simply adding energy levels and getting farther and farther away from the nucleus. Okay. So we're going to talk a little bit about sizes of ions. They're a little bit different. So let's look across energy level or period 2 on the periodic table. Okay, and in that you have lithium, beryllium, boron, oxygen, and fluorine. I left out the transition metals. Well, actually, there are no transition metals in group 2. So those are the group 2 atoms. So hopefully you remember when we talked about ions that group 1A, 2A, and 3A all tend to lose their valence electrons and become cations. Okay, so group 1A tends to have charges of +1, group 2A +2, group 3A as ions have charges of +3. And then if you get to group 6A, the oxygen group, they tend to gain, well, the nonmetals, or the groups 5, 6, and 7, tend to gain electrons and become anions, or negatively charged. Okay, and the oxygen group takes on a charge of -2. The halogens take on a charge of -1 when they're ions. All right, so the first thing I want you to understand about the size of ions are that cations are always smaller than the neutral atom they come from. Makes sense, right? You're removing an electron. It's a little bit more complicated than that, but that's certainly an easy way to remember it. So it's not simply that you're removing an electron, but when you're making a cation, you're typically removing all of the valence electrons. What happens when you remove all the valence electrons? You completely have removed an energy level. So typically when you make a cation, you remove the entire outer energy level, making that whole resulting ion much smaller than the original neutral atom. All right, onward to anions. Anions, just the opposite of cations, so the anions are in blue here. Okay, those are going to tend to be larger than, well, they always are larger than the neutral atoms they come from. So if you haven't already noticed in these visuals, the core sphere in all of these visuals is supposed to represent the neutral atom, and the larger half sphere is supposed to represent the relative size of the ion that's made from it. So you can tell in each case the size of the anion is larger than the original neutral atom, and that's, so many students forget this because it sounds trivia, but I would write that down, put it someplace where you can review it, because I can almost guarantee that's going to show up on your test, maybe as a multiple choice and also as a possible conceptual short essay question. So why are anions larger than the neutral atom they come from? Because by adding extra electrons, we have increased the repulsion between all of the electrons. And what do things do when they're repulsed from one another? They spread out, they try to get away from each other. And that results in a larger atom. All right, so kind of to summarize the trends, going down a group or across a period. Okay, let's talk about going down first because that's kind of easier. The trend of size going down is the same as it was for atoms. Okay, you're adding energy levels. With each step down, you're adding another energy level, electron energy level, so they're by nature just larger and larger and larger. The trend across a period, as you can see, is not a real steady trend. Okay, remember, if we're talking about atomic radii trend, not an ion, but just the neutral atom, the trend went down. Here you see it kind of looks like it goes down and then it goes back up. And that's because group 1A, 2A, and 3A make cations, so they're going to get smaller, smaller, smaller. And then as soon as you get to the group that makes the anion, and I don't know why they left out group 5A. There must be a lot of anomalies here. But notice when you jump from the group that makes cations to the group that makes anions, you have quite a huge jump in the size of the ion. So just be aware of that. And then once you start making anions, that trend of getting smaller as you go left to right continues. In other words, the anion from fluorine is in fact smaller than the anion from oxygen. Okay, but both of them are larger than any of the cations in that period. All right, so a very common type of question that you'll be asked to tackle is this one. Okay, so pay attention, understand this slide. There's something called an isoelectronic series. You may know that when you see the prefix iso, that tends to mean the same. Okay, so if you see isoelectronic series, it means atoms that have the same number of electrons. Okay, you'll run into that when you're talking about ions. Okay, because hopefully you remember this, but any ion will tend to either lose or gain electrons so that it has the same number of electrons as the nearest noble gas. Okay, and so because of that, you'll often run into what we call an isoelectronic series of ions, where you have a whole bunch of ions and they all have the same number of electrons. That's the case with the isoelectronic series shown here. All of these ions have the same number of electrons as the noble gas neon. And neon has 10 electrons. So all of these have 10 electrons. And so you might be asked a question that says, rank or order all of these ions from the smallest to the largest, or the largest to the smallest. Okay? If they have the same number of electrons, the only thing you need to be concerned with in ranking their size is the number of protons each of them has. Okay? The larger the number of protons, okay, so as the number of protons increases, the smaller the ion. Okay, if it's an isoelectronic series. Okay, if all other things are equal, they're all in the same energy level now. They all have the same number of rings or energy levels around them, and the only thing that matters is the number of protons. And so, which one of these, sodium, magnesium, aluminum, oxygen, or fluorine, have the most number of protons? Well, you would need to look at a periodic table, because my guess is you probably haven't memorized where they're placed. But I'll just write them in right now. So neon has its atomic number 10, so it has 10 protons too, in addition to neutrons. Fluorine has 9 electrons. Oxygen has 8. I'm talking about protons. I'm flipping back and forth. Fluorine has 9 protons. Oxygen has 8 protons. Aluminum has 13 protons. And let's see, magnesium has 12. And sodium has 11. Okay? And so in an isoelectronic series, the ion with the largest number of protons will be the smallest. So aluminum is the smallest. And then magnesium next, a little bit bigger than aluminum ion. And then sodium. Okay. All right, so now if you're paying attention to the number of protons that I wrote for each of these, okay, we've taken care of 13, 12, 11. Remember that if the noble gas is included in the isoelectronic series, you would have to include it, and it would go right there in between the cations and anions. In this case, it wasn't included, but I just wanted to point it out. And then it would be fluorine, and the very largest one in this isoelectronic series would be oxygen. So here's a very typical question for you, and as always, I strongly recommend that you turn off the video for a few minutes and see if you can answer these questions on your own, and then come back and I will give you the answer. All right, with the thought process on arranging these neutral atoms in order of size, you have to remember the trends going across a period and down a group. If you were to draw just one line for the trend of atomic radius, basically the largest atom is in the lower left and the smallest is in the upper right. And so the trend would look something like this, where the atoms would get larger as they approach the lower left and smaller as they approach the upper right. So if you look at where phosphorus, sulfur, arsenic, and selenium are on the periodic table, my wonderful artistry skills, okay, they're kind of in this little square here, okay, where you've got phosphorus, sulfur in the same row, and then right below them you have arsenic and selenium, okay. And so obviously arsenic and selenium are going to be larger because they're farther down, okay. But which one of these, arsenic or selenium, is going to be the largest? Now you have to remember that as you go left to right across a period, the atomic size gets smaller. So selenium is actually going to be smaller than arsenic. So arsenic again is the closest to the lower left, so it's the largest. So we're going to place it here. Then because selenium is in the lower, a larger period, it's going to be larger than the other two above it. Same trend when you're comparing phosphorus and sulfur. Sulfur is going to be smaller. Remember, the atoms get smaller as they go left to right. So sulfur is actually going to be the smallest, okay, and phosphorus is in the middle. So the correct trend, ordering these from smallest to largest, sulfur, phosphorus, selenium, arsenic. Be careful because some of these questions will ask you to arrange them from largest to smallest. And so read the wording very carefully. The first thing I do when I'm looking at ions is I'm checking to see if they are in fact an isoelectronic series. Do they all have the same number of electrons? Because if that's the case, I'm just going to compare the number of protons they all have. So potassium starts out with 19 electrons. It has +1, which means it's lost 1 electron. So at this point it has 18 electrons. Calcium starts at 20 electrons, has lost 2. It's also 18 electrons. Chloride starts with 17 electrons, but it's gained 1. So it has 18 electrons. It looks like we have an isoelectronic series here. And in fact, we do. So all of these ions have 18 electrons, which is the number of electrons that the noble gas argon has. And so the question asks you to arrange them from smallest to largest. The smallest ion will be the one with the largest number of protons, okay, because it'll have the strongest attraction and it'll draw the outer electrons in the most strongly. So I think I said electrons, the largest number of protons. So look on the periodic table and find out which one of these has the largest number of protons. And I'm going to write the atomic number for each of them above them. So potassium has an atomic number 19, calcium 20, chlorine has an atomic number 17, and sulfur is 16. The smallest one will have the largest number of protons. That's calcium. And then just go in order of protons. So sulfur is the largest ion here because it has the fewest number of protons. All right, that's it for this lecture. There won't be an individual quiz on atomic size. I'll wait and give one quiz over all of the periodic trends.